Welcome back to another session. What I would like to do now is talk about sketching a Bode plot, and I have a particular example in mind. It's g of s is equal to s plus 10 up in the numerator, and in the denominator we have two factors that are real. One is at s plus 1 and the other factor is s plus 100. I think before we even hardly get started with the solution, I'm hoping that by now you can see that this transfer function is in what I'm calling the pole zero form, and in order to sketch this with a Bode plot, what I like to do is to convert the pole zero form or any other form into time constant form. And in so doing, what we're doing is we're normalizing the constant coefficient's value to 1 and collecting all of the parameters that might be varying in our discussion into one particular location in each factor. Let's now get started, and all we really need to do is factor the constant coefficient out from each term. I'll be very explicit with factoring the constant coefficient out, even though in the s plus 1 it really doesn't need to be factored out. We've now factored all of our constants to a format to set those equal to 1. We can now collect our constants out front. We have 0.1 s over 10 plus 1, or we now have a 0 at s equal minus 10. We have a pole at s equal minus 1, and we have another pole at s equal minus 100. To sketch the Bode plot, we're now looking at not g of s, but we're looking at g of s evaluated along the imaginary axis, or we're now looking at g of s, the transfer function, with the complex variable s replaced with j omega, or restricting our attention to evaluating that transfer function right along the imaginary axis. We now have 0.1 j omega over 100 plus 1, j omega over 1 plus 1, j omega over 100 plus 1. And now what varies is this omega from 0 to infinity. Our second step that I'm collecting is in this process of solving or sketching the Bode plot is really just what I want to make or classify as observations before I even start sketching. And the reason I'm doing this is to allow me a way of checking as I go along to make sure that I'm starting in the right place, or that I'm ending up in the right place, or really what do I expect, or what to expect when we're sketching this Bode plot. There's several things that we can observe in this process. One is that the absence of something, and the absence of what I'm looking for is there is no pole or finite zero at the origin. There's no s term in the initial transfer function in the numerator by itself or in the denominator by itself. What that allows us to say, and the other thing that, well, with no pole or zero, let me just continue with that thought. With no pole or zero at the origin, then our phase curve begins at 0 degrees for small frequencies. Now we know where to start our phase plot. We can also find the low frequency gain, or in this case the DC gain, which is 0.1, because we have no pole or zero at the origin, we're not forced to have a gain of 0 if we had a 0 at the origin at DC, or an infinite gain if we had a pole at the origin. So with no pole or 0 at the origin, we not only have a phase beginning at 0 degrees, but our absolute gain value we know, and it is actually, in this case, it's a positive 1/10, and that gives us then a value or a straight line that we will be beginning our magnitude plot with. We can also, with this particular transfer function, examine how many poles we have relative to the number of zeros. And if you look, we have 2 finite poles versus 1 finite zero, or what I like to call the pole zero excess. How many more poles do we have than zeros? And I typically refer to the number of poles as the variable p, the number of finite zeros as z, and that's 1. With that particular observation, we can make several facts known to us as we're sketching. We know that the phase eventually, for high frequencies, will end relative to this pole zero excess value. We have one more pole than 0 in the limit, or now, and so in the limit, as we get to large frequencies, the phase is going to favor the look of, or look like, a single pole system. So our phase will end at the phase of a single pole, which is minus 90 degrees for large frequencies. We also know, based on the behavior of the Bode plot at large frequencies, if we have one more pole than 0, then we know what our magnitude is going to do at large frequencies. Our magnitude is going to slope like a single pole at high frequencies, or it's going to slope at minus 90 degrees, or I'm sorry, just getting hung up on the line above, but it's now going to slope at minus 20 dB per decade. And this is the pole zero excess value. It's going to just do minus 20 dB per decade, since we have a pole zero excess of 1. We will be sloping then our magnitude at minus 20 dB per decade for large frequencies. The other thing that we can realize is, with no poles or zeros at the origin, we actually can say that our beginning magnitude is going to be flat. For low frequencies, or constant. Magnitude will be flat at low frequencies until we hit our first break frequency, and I think it's clear where our first break frequency is in this particular, at low frequencies, until we hit the first break frequency. Now that we have those observations, let's go ahead and even before we start sketching, let's just write down or describe the contributions of each of these factors or each of these terms in our transfer function expression. We have our constant term, and each of these terms has a magnitude and phase component. For the magnitude of our constant, that's just 20 times the base 10 log of the factor that we factored out, or the constant that we obtained, which is 0.1, or that's 20 times the log base 10 of 10 to the minus 1, or that's minus 20 log base 10 of 10, which is just minus 20 dB, and that's for all frequencies omega. Our phase of that constant, because it's a positive real number, is going to be 0 degrees for all frequencies. And what I like to do in looking at these terms, if I can, I like to work my way from lowest frequency to the highest frequency. In doing that, we have our constant, obviously, term, and then we, in this particular transfer function, the first break that we come to is a pole, and that is our pole at s equal minus 1. That has the two pieces. It has a magnitude piece, which will be 0 dB until we reach the break frequency, and that's why we've highlighted that, and it's going to break at 1 radian per second. After it breaks, it then maintains a slope due to that particular factor, and it's just one pole at that frequency, and so our slope is going to be minus 20 dB per decade after it is sloped. The phase will kick in and kick off. I like to identify the kick in and the kick off frequency locations, and the midpoint of that turning on and turning off. The midpoint actually occurs right at the break frequency. The turn on occurs a decade before the break. The turn off occurs a decade after the break. And using those conditions, I end up with the phase of this particular factor will be 0 degrees with omega a decade below the break, which is at 0.1 radians per second, a decade before the break, which was at 1 radian per second. We will actually be, because it's a pole and downstairs, a minus 45 degrees when we are right at the break frequency. And we will, in these approximations, straight line approximations, we're going to assume that we're right at the limiting value of what the phase contribution can be to this single pole factor, which is minus 90 degrees when we are now a decade beyond the break frequency. The next factor that we come to is actually our zero factor in terms of frequency from lowest to highest. This is now a 0 at s equal to minus 10. We have our magnitude, which will be 0 dB until we reach the break, and the break is going to occur at 10 radians per second. After that break, this particular factor will give us a slope, since it's in the numerator or upstairs, of 20 dB per decade thereafter, and it will never shut off, that particular slope in the magnitude. I make that comment because in the phase you have to worry about it turning on and turning off. And since it's in the numerator, it's going to contribute at most 90 degrees. It will be 0 degrees a decade before the break frequency, or it's going to start its slope change at 1 radian per second. It will be contributing plus 45 degrees right at the break frequency, which is 10 radians per second. And it will have contributed in this straight line approximation its maximum phase a decade above the break frequency, or by 100 radians per second, we will have in our straight line approximation this zero factor giving us all of its 90 degrees. We then only have the one more pole left, which is our pole at s equal to minus 100. And I think now hopefully you're starting to get the hang of what I'm doing with my description. It's going to be 0 dB until we hit the break. And the break again is at 100 radians per second. After the break, it's going to slope. It's a pole, it's downstairs. It's going to give us this minus 20 dB per decade slope all the time after the break frequency. Our phase, a single factor or a single linear factor, is going to just give us 90 degrees, and since it's downstairs, it's only going to give us a negative 90 degrees. It's going to start contributing phase a decade before the break frequency, or actually at 10 radians per second. Right at the break frequency, or 100 radians per second, it will be contributing minus 45 degrees of phase. And by the time we get a decade above or beyond the break frequency, or at 1,000 radians per second, this particular factor will be contributing all of its phase amount, which is minus 90 degrees. Now we're able to go ahead and sketch all of these pieces that we've just listed in writing to allow us to maybe more effectively sketch the magnitude and phase plots for this particular diagram, or for this transfer function. I now have some 6-cycle log paper. Let's say that this is now going to be the magnitude of G in dB. And if you remember where we were starting, we actually can go back and find that we did not have a pole or zero at the origin, which now says that at low frequencies we're just going to have the magnitude associated with our gain, or our constant, which is minus 20 dB. And the first bend that we will have, or adjustment in our magnitude and phase, is going to occur at 0.1 radians per second, which is due to the pole at 1 radian per second. So really we only have to start our frequency axis. Here's our frequency axis, omega. Let's say this is now 10 to the minus 1. Here's 10 to the minus 2. Up. Want to go in the other direction. This is going to be 1. Here's 10. Here's 100. And here's 1,000. And that's really about as far as we need to go in this particular example. If this curve, or this particular boulder line, is what we will refer to as 0 dB, and here's minus 20, minus 40, minus 60 dB, here's plus 20, what we are going to do with our constant piece, how about if I do that in a slightly less bold line? Our constant is going to give us minus 20 dB for all frequencies. Then in terms of our magnitude, the first thing that we are going to have happen is our pole at 1 is going to kick in, and it's going to contribute a negative 20 dB per decade slope. The next factor to kick in is our 0 and so now we're coming down. We were 0 until we reached 1 in our slope of the magnitude, and then we would keep going, except now in this particular example we have a 0 that occurs at 10, and because of that we cancel effectively this slope change of minus 20 dB per decade. Then we go flat until we reach our next pole, and our next pole is at 100, and because of that then we have a flat magnitude plot, but thereafter we are going down 20 dB due to the first pole. We're going up 20 dB per decade due to the first 0, which causes us to go flat, and finally then we have another pole that contributes a minus 20 dB, and so now we're going minus 20 dB thereafter for all frequencies beyond 100 radians per second. And if I sketch that now in red, hopefully the final magnitude plot will then be the sum of all of these contributions, which is really sort of what I put together anyway. And now let me just go ahead and complete that magnitude Bode plot, which is now sloping at minus 20 dB per decade beyond 100 radians per second. In the phased plot, if we keep the same axis labels for our frequency omega, then this particular frequency is 10 to the minus 1. Here's 1, 10, 100, and 1,000. We remember that we were starting at a phase of 0 degrees. Here's our phase of G. Let's say this is plus 90 degrees and this is minus 90 degrees and minus 180 degrees, and we should remember that we're starting at 0 degrees, and we said we were going to end at minus 90 degrees for large frequencies. And so we are going to then end up here at our minus 90 degree curve. We're going to start at 0, and sometimes what I like to do is actually indicate that I'm going to then have a 0 kick in at 0.1, and it will turn off a decade above the break, which was at 1. I had a 0 factor that was going to kick in at a decade below its break, which the break was at 10, so a decade before that is going to be at 1. We then have it turning off its slope change a decade beyond its break. And finally, we have another pole factor kicking in a decade before 100 and a decade after 100. And I'll try to now sketch those contributions as I go. Or now I have this this pole at 1 giving us, or giving rise to, a minus 90-degree change over those two frequencies, or those 2 decades of frequency change. And so it would look like that if nothing else happened. But because the 0 kicks in halfway through that transition, the 0, if I draw it in, is starting here and ending here. And the last factor is the 0 factor that begins at 10 and ends at 1,000. And now what we want to do is sketch all of those together, or their contributions, meaning now we have the pole, the first pole, going down, then the slope of the 0 and the slope of the pole cancel, and we're now flat. The first pole kicks off at 10, but the second pole begins to kick in at that point, so we're still sloping down with a negative minus 45 degrees per decade with poles, but we're sloping up with the 0 at that point by that same amount. And so now we continue flat. The 0 quits contributing a slope beyond 100, but the pole that is still there, the last pole that had a break at 100, now continues to contribute phase until 1,000, and then it stops, and we now have our final phase curve, which, let's see if I can, maybe I'll just highlight it, is now going down at minus 45 degrees per decade until we reach 1, and then it goes and it's flat until we go all the way out to 100. Then it continues to go down at minus 45 degrees per decade until 1,000, and at that point it's minus 90 degrees thereafter. That completes this discussion of sketching the Bode plot for our original transfer function g of s, which, if I can find my notes, was simply s plus 10 as the numerator factor over 2 denominator factors, or 2 real poles, one at minus 1 and one at 100. We had a phase curve that looks highlighted in yellow. It starts at 0 degrees and ends at minus 90 and transitions somewhat smoothly between those two limiting values. And our magnitude plot begins at minus 20, goes down, then goes flat, and finally goes down at minus 20 dB per decade for all frequencies beyond 100. That's the Bode plot for this nominal system. What if we wanted to ask some more questions, or maybe we weren't happy with what that frequency response looked like? Or what if we wanted to change or modify this transfer function? And in particular, suppose that somebody said, you know what, I don't like the fact that our low frequency gain is minus 20 dB, or that we have a gain in absolute sense of 0.1 for low frequencies, or maybe for all frequencies, and so they say, what if we increase the gain for all frequencies? and maybe they tell us what they want it to be. We want to now modify the original transfer function and create a g bar of s, and we want that to be 10 times the original g of s. Or now, because we are increasing the gain by a factor of 10, it was at 0.1, we now are wanting a DC gain of 1 instead of 0.1. Or if we wanted to look at the gain of g bar of s when s is equal to 0 for the DC gain, that's now equal to 1. This isn't too hard to visualize as far as what that means in terms of our original plot. All that is saying really is that we need to raise the magnitude plot and leave the phase plot unchanged. If all we're doing is introducing a gain, then this raises the magnitude plot by a fixed or constant amount of 20 times the log base 10 of 10, or 20 dB for all frequencies. And that just means that if we went back to our magnitude plot, we would simply need to move this entire curve up 20 dB. And that's what the magnitude plot would look like. The phase plot would remain unchanged because a constant of 10 scaling our original transfer function is not going to change the phase in any way. And so the second observation is that this gain change does not change the phase curve. At any frequency. What if that's not really what we wanted? Maybe we wanted to modify the original transfer function in another way. Suppose we wanted to introduce a pole at the origin. And your first thought is, why would we want to do that? Well, we may actually want a large gain at low frequencies. And I'm sure you're saying, I still don't understand why we would want to do that. Well, as you go on in your coursework, hopefully this will become clear when you take, for example, a controls class. In a controls setting, you may want to have a high frequency gain at low frequencies to zero an error signal. If you were trying to track a constant input waveform or reference signal, it might be to your advantage to have a high gain at that low frequency or at constant frequency, and that's what you could do by introducing a pole at the origin or a pole at 0. The change that would do is if we now have a pole at the origin, that's going to change our phase curve, and it's actually going to lower the phase curve a fixed amount for all frequencies, and it's going to lower it by 90 degrees. Or another way of saying that is just let's move the phase curve, shift it down, or move the phase curve minus 90 degrees. The magnitude plot is a little bit more interesting, but really all it's doing is introducing a minus 20 dB per decade shift or slope change throughout the gain curve. And if I could go back to our original Bode plot, our phase curve didn't change. Our magnitude curve, let me see if this is going to allow me to erase my highlighted curve from before. May or may not want to cooperate. And it's going to erase everything, but that's okay. What I want to do now is show that really this particular pole at the origin is going to cause my system to experience a new change in that we're now adding everywhere this slope of minus 20 dB per decade, which means that if we add that plus 20 to minus 20, we are now effectively starting right there at a frequency of 1. We are going to be at 0 dB due to the pole at the origin and minus 20 because of the original curve. Then at a frequency of 10, we will have, due to the pole at the origin, a minus 20 dB contribution. We're already at minus 40. That means we'll be at a minus 40 plus a minus 20, or a minus 60. Then at 100, we're no longer going to be flat between 10 and 100 because of this pole's influence. We'll be sloping at 20 dB per decade, so we'll go down to minus 80 dB at 100. And then after that 100, if we just looked at 1,000, I now have minus 60 plus another minus 60, or that's going to be minus 120. If I say this was 100 and this is now minus 120, I now am sloping at 40 dB per decade after the original slope of minus 20. Here's another 40 dB change, and here is 20 dB change. And so the purple highlight is now what would happen to our phase curve. Our magnitude curve. The phase curve is simply going to be changed such that we add minus 90 degrees everywhere to it. So we'll be here. We now are at minus 90. Then we go down to minus 135. We remain flat until we reach 100, and then we start going down again. And finally we end up at minus 180 for our next modified phase curve. That should be enough changing to the original Bode plot, but I hope that gives you an idea of how you can now play with the information that you have on Bode plots and how to quickly sketch and think about what those mean.